in the macroscopic world that we're used to seeing things with, I think something this pen can have a continuous number of energy levels. But in the microscopic atomic world, an atom or a microscopic particle can only have discrete levels. It can only be here or here. It can't be somewhere in between there. It's discrete. So the electron here, the proton electron, the electron can't be somewhere between there. It's got to be there or there or there. It's distinct places. So we have to think about things as quantum, not continuous. For a real particle, we can think about the total energy being the kinetic and potential energy is a function of the separation of these parts, and they can only exist in certain discrete levels. And so this delta energy level is this quantum energy level. And so we can think about something really, really simple like a hydrogen atom. And so for a hydrogen atom, proton electron, this proton electron, they're oppositely charged. So therefore they attract each other. They have an electric potential, Q1, Q2, or 4 pi epsilon 0 r. They're both charged of one's plus E, one is minus E as far as coulombs. And so this becomes a minus, meaning they're attracting, like gravitational, is minus E squared 4 pi epsilon 0 over r. And if it's a macroscopic thing, then these levels could be any continuous thing. But for the microscopic hydrogen atom, there's only discrete separations they can exist at. So there's only discrete energy levels that can exist. And the lowest one is called the ground state. And for a hydrogen atom, for any state, the energy of the hydrogen atom is minus a energy term, electron volts, 13.6 electron volts, very, very small, divided by the state number squared. So in the ground state, which is state 1, the energy level is minus 13.6 electron volts. And then at the next energy level, 2, it's this divided by 2 squared or 4, is 13.4. And then this divided by 9. And you can see that the separation distance for it between different energy levels of a hydrogen atom is they're getting closer together, less energy difference as I go away from the ground state. And so that's this. Now for a real molecule, it's more complex, but sometimes we model things to try to get a close understanding what it is. And so one model that helps us is to think about a harmonic oscillator. So that's just a simple spring in a mass system, and that can have different levels of energy depending on how much you pull it off. So macroscopically, if I just have this sitting here and it's in its rest condition and it's not moving, it's going to be at its lowest energy state. And then if I pull it away some distance, I give it potential energy and I let go. So I gave it some potential energy. So I start to climb up here. I go from there to some potential energy state, and then I let go, and then it's going to stay at some total energy level for just this, because I have no losses for just this real simple oscillator. I'm just going from potential to kinetic back to potential and keep staying on this line. And for a macroscope, I think I can pull this continuous amount. I don't have to be discrete levels. But for a microscopic particle, there's only discrete levels I can pull it. I can't pull it a tiny bit. I got to pull it all the way to this next I got to pull from this level to that level. I can't stop anywhere between, because it's a quantum thing. It's a microscopic thing. And so thinking about this harmonic oscillator to help us with the model, we know that the angular frequency of this is omega sub 0, which is the square root of the interatomic stiffness divided by, for atom, interatomic stiffness of the atom divided by the mass of atom. So that's my frequency I'm gonna oscillate. And for this model, we found that the difference in levels is proportional to this term right here. So jumping between levels, from ground level to level 2, and from 2 to 3, and 3 to 4, etc. Every one, there's a discrete uniform spacing of energy level, which is which is h bar times this angular frequency. And then the ground level is h bar over 2 times this angular frequency, or the square root of KSI over MI. So for this one, for this simple harmonic oscillator modeling a microscopic particle, we have these discrete, continuous, discrete levels, definitely not continuous, discrete levels of energy levels. And here, h bar is what's called Planck's constant over 2 pi. And h bar has units of joules per second because it's being multiplied by joules seconds. So they're both in the numerator. Joule second. So joule second times radians per second give us joules, because radians is unitless. So this term right here is h bar omega 0 is units of joules. So these are different discrete levels of joules. For this model also helps us thinking about if the interatomic stiffness is high, which means I pull it back a little bit and I get a big change in potential energy. So this is a steep thing, because for any little distance I move away from my s equals 0 to some different separation, I get lots of potential energy before I let go of it. So then the energy level difference is large. For one that has low stiffness, there's low change in energy with the separation, and my omega 0 small and my things are set close together. So now that we've thought about things as being quantum, and I know for microscopic things, and they have to be at discrete levels, how does that help me? Well, I can have interaction things changing. For example, I can absorb a photon. So I have, example, either a harmonic oscillator I can model as a hydrogen atom, and I'm at some state. Let's say I'm at some state right here, so say ground state, and then a photon hits it, but it has to be the photon with the exact right quantum level to jump me up to here. If that photon has this energy level, then it'll jump me up to here. But if it's somewhere between there, then it won't work because I don't have the exact amount of energy. So if I think about a photon coming in, so let's say my ground state here, and this photon comes with this exact amount, the delta energy here, of 10.2 electron volts. So this photon comes with 10.2 electron volts. I can jump to there. So thinking about as far as energy, our energy principle, system, an atom, and a proton, the energy final equals an energy initial plus work plus heat transfer. I'm not going to have any work. I'm not going to have any heat transfer, so those both go away. So I know my total energy final is my initial energy. Well, in the final state, I had this atom at this condition, and now I'm going to absorb a photon, so I just end up with an atom. So this is going to be the energy of that atom in the final state. And coming in, I had the energy atom here plus the K of the photon. So what happened? So I started out here. I absorbed this energy from the photon. I went to that final energy state, and there's my energy balance. The same thing. I can emit photons as well. So I started, for example, I could say I started at this energy level, and I emit a photon, and I go down to that energy level. The photon energy level is a discrete quantity that has to be there. It's not continuous, it's discrete. So thinking about energy again, energy final is equals energy initial of the system. Finally, I emitted something. Finally, I had an atom down here at that final state, and I had a photon at some energy level, and initially I had the atom at that level. So I can find the K photon equals, atom initial minus the energy of the atom final. So that the delta energy here is the energy of that photon emitted. I talked about photons. What is a photon? A photon is a particle of light. It has zero rest energy, so it has no mass. Rest energy mc squared. It has no rest energy, so it only has kinetic energy, and it always travels the speed of light. And a photon, whether it's X-ray, a red light, red colored light, or green or something, that has certain energy level. So it has certain energy level because it only has kinetic energy, and that energy level is related to this Planck's constant times the speed of light divided by the wavelength. So something that has short wavelength has lots of energy. Something that has large wavelength has small energy as far as a photon. And further thinking about this is for particles. For a particle like a photon, the total energy is gamma mc squared, where gamma is 1 over square root of 1 minus the velocity over c squared. For a particle, the Charles speed, we know that the total energy squared minus the square of the potential energy times speed of light squared equals this invariant quantity called to the rest energy squared. And for a particle of zero mass like a proton, zero rest mass, this goes to 0 then. So we have e squared minus momentum, the quantity momentum plus c squared equals 0. So for a particle of zero mass like a photon, E equals pc, or momentum equals e over c. There's also a relationship between temperature and in the state that's in. The lower the ground state, the lower the temperature, and we'll talk about that in the next video.